We will see gradient vector concept from the Cartesian point of view and from the spherical coordinate point of view. So these are the two things that brings the gradient vector. Okay, so why all of a sudden the gradient vector is in picture again? So that is the question. So what we have done, we have already seen that there are many coordinate systems like uh, Cartesian coordinate system XYZ. We have polar coordinate system in 2D. Then in 3D, polar to cylindrical coordinate system. And then we have a spherical coordinate system. But miss, we were quite till we saw a different coordinate system. Now, when we have seen vector calculus, then kind of one greediness, one kind of curiosity that arrives in mind that if I know now if I have points and they are in vectors, earlier if we see the algebraic equation and with that, if I have xy point, as per the xy point, either we have density or we have the other orthogonal component like z. So fxy equal to z or fxy equal to the surface density. This is what we saw. But other thing that came into the picture that rather than we have value for each x comma y, now x, for each x comma y we have vectors. Okay, and that's the way the parametric vector in calculus came into the picture. So now the general equation for any line or surface we have in the form of vector. So direction is, when direction is there, then we will see how gradient vector look when we see it from the parametric vector point of view. Okay, so now question arrives that if I see things through parametric point of view, then how it differs when we are seeing from the kind of algebraic point of view. So algebraic point of view and Cartesian uh, Cartesian coordinate system and parametric vector point of view, then a spherical coordinate system. So that is the idea. So now let's begin with the parametric vector point of view, calculating the gradient vector as far as a spherical coordinate system is concerned. So that is the idea that we would see. Now, what is a spherical coordinate system? Okay, so okay, so suppose this is a sphere. This is a sphere. If this is a sphere, then from here, from here, I am taking out a line vertical. So here, and it will come out here. So there is a line that passed from here and it would come out here. There is a line. This is the sphere. Now the scenario is If this is the line that is passing from the center of the sphere, then if it rotates like this in one plane, okay, if it rotates like this, then this angle, can we see now it is vertical and this angle is phi. Phi is 90 degree and phi is 180 degree. So phi varies from 0 degree to 180 degree. Now if I take any time the phi as constant, suppose phi is 90 degree constant, then if I rotate like this, then this is theta degree. So at any phi constant that is 90 degree, then this is theta degree. It rotated. And whatever we are seeing this is radius. So radius, if it is small, then this big sphere. If radius is big, then this big sphere. So if I see 3D Cartesian coordinate, then we have x, y, z. But if we see 3D spherical coordinate, then we have radius, we have phi, and then we have theta. These are the three orthogonal components. So now any point, any point in Cartesian coordinate, I can address it as fxyz function over xyz. So xyz is the any point I can address, and density function over fxy xyz at the point xyz, what is the density? That is fxyz function over x, y, and z. So now here any point on the surface, it is r, phi, and theta. So r is the radius that describes the how big the sphere is, phi angle from the vertical, and then it rotates like this, theta. So theta rotates 2 pi, phi rotates 0 to pi, r rotates 0 to a, where a is the radius. Now this is a spherical coordinate system. Now if this is a spherical coordinate system, that any point, if I keep the theta constant, okay, now if theta is constant and r constant, theta theta constant. Now only phi is moving. So phi like this. Okay. If phi is moving, then I have at any point, if I see the z component, I mean I am mixing Cartesian now. So the vertical component, this component is a, if this is a cos phi. Okay. This component is a sine phi. There are two components that we are seeing. One is vertical component. I want to say z-axis vertical component. So if this is radius and this is phi, then a cos phi. And if this is radius and this is along the horizontal axis plane, then this is a sine phi, where the theta, so if this is rotating like this, then at any moment if this is 0 degree theta, then it is at angle theta. Theta is 90, theta is 180, theta is 270, and theta is 0 degree. This is at theta. Okay, so if this is at theta, then this length, whatever the length we are seeing, that is a sine phi, and this is horizontal component, and this is a cos phi, a cos phi, and a sine phi. Now if I have a sphere, if I have a sphere, that at any point r theta phi or r phi theta, any point r phi theta, then what would be the gradient vector? Means if I say gradient vector, then it is something like we are trying to calculate the kind of dz, means slope, along x-axis, y-axis, and z-axis. So we are taking help of a spherical coordinate system. So if I have a kind of any point, so this if suppose, so we are addressing this point as r, phi, and theta. Accordingly, there is a point in Cartesian system as x, y, and z, x-axis, y-axis, and z-axis. If I say that I want gradient at this location, typically gradient will be either it is tangential or it will be perpendicular. Okay, if that is the case, then how gradient looks? Now if I'm considering any point here, that is x, y, z, or r, phi, theta, any point at this point, so this point is x, y, z, or r, phi, theta. At this point I have to calculate the gradient. Gradients means d delta. If function here is fxyz, then delta fxyz, delta d, delta density. Okay, so d fxyz equal to then x component whatever we see. Okay, so dfxyz equal to dfxyz by dxi plus dfxyz by dyj plus dfxy by dfxz by dzk. These are the three kind of component of the gradient vector. If I have a function fxyz, we also call it density function. If I have a function fxyz, then the kind of, if I want to calculate the gradient at xyz, then that will be dfxyz by dx along y-axis, dfxy dz by dfxyz by dy along z-axis, j-axis, y-axis, and dfxz by dz along k-axis, z-axis, dfxyz by dxi plus dfxyz by dyj plus dfxyz by dzk. So this is the gradient vector in 3D or 4D also you can say. Now if I come through a spherical way, then the xyz point is now r, phi, and theta. The three orthogonal components are r, phi, and theta. Now if this is r, then k means vertical is r cos phi, whereas along the horizontal plane, xy plane, it is r sin phi, r sin phi. Now if it is a theta here, then r sin phi cos theta I plus r sin phi sin theta j. So three components, if I convert a spherical to coordinate, a spherical to Cartesian coordinate, then it will become r or a. If a is the radius, a cos phi, and then a sin phi cos theta, a sin phi sin theta. So it will come as a sin phi cos theta I plus a sin phi sin theta j plus a cos phi k. Okay, so this is what the kind of a point that is equivalent to xyz. So if I say what is xyz, if I have r, phi, and theta in a spherical coordinate, then xyz at any point is, as per r, phi, and theta, is r or a. If it is a radius is a, then a a sin phi cos theta I, x component is a sin phi cos theta I, a sin phi sin theta j, a cos phi k. So z component, the z component is a cos phi, whereas I component, x component is a sin phi cos theta, and y component x component, and I means x component, j component means y component, a sine phi sine theta. Now question arrives is what would be kind of the the gradient vector. Okay, if this is the kind of we have the function. Okay, so fxy is the function's x component is like this, y component is like this, and z component is like this. Okay, rather than saying it is x y z component, okay, we can say that this is a kind of a function. If I try to calculate the derivative now, okay, so the if I see the equation of function now, consider little closely. Now suppose that now I am taking theta. This is theta that rotates in 2 pi. Now theta, I have taken theta as constant. If theta is constant, then phi would vary from 0 to 2 pi. Let's take theta as 0. If theta is 0, then story is within zx plane. If theta is 0, then story is in z x x z plane. If it is story is in xz plane, then at any phi angle, the x is a sine phi. So I can say a sine phi I plus a cos phi k. If this is the kind of we have x component of the function and k component of the function. So we are talking about this circle. In xz plane, we are talking about the circle where at each point in the circle is described as a sine phi I plus a cos phi j. So we have displacement vector. Okay, now if we come to parametric equation, then we have displacement vector. So at any point, if I rotate in xz plane where theta is 0 and phi is rotated. So if that is the case, then at any point, okay, the horizontal component, if this is phi, then a sine phi and other component, because it is 2D, I have made it 2D, where phi is 0. So, whereas this vertical component is a cos phi. So, this particular point, when I am rotating, this particular point is addressed as a sine phi I plus a cos phi k. If that is the case, then the position vector here, then this point is radial. First, this is greatness of the parametric vector in calculus. Everything has a direction. If I say, if I have a kind of x square plus z square equal to a square, that will come in Cartesian coordinate. X square plus z square equal to a square, I don't know the direction. Probably direction will be point. It is set of points and that has no direction. So I can say circular direction or whatever. But if it is parametric vector, and if I say it is a sine phi I plus a cos phi j, then each point if I see, then it is a radial vector. I can prove it. So if phi is 0, means here if phi is 0, then only k component exists because sine 0 is 0. So it is in vertical direction. When phi is 90 degree, then only sine will exist, cos will go away. So it is in this direction, that is I direction, a sine 90 degree I. So it is in this. So this is radial everywhere. Now I had taken theta 0. For any theta now I can take. If it is like this, then this this circle we are talking about. If theta is 90 degree here, then keep theta constant, then vary the phi like this. Okay. And if theta is 45 degree, then vary the phi like this. If theta is 0 degree, that what we are taking, then it is pure xz plane. The vary the phi like this. So now I have equation displacement equation in the parametric vector form is a sin phi I plus a cos phi j cos phi k if I have taken theta as 0. Now we will calculate the gradient vector. If we calculate the gradient vector, okay, in xz plane, then I have to differentiate it. Now I am ready to differentiate. So gradient vector will differentiate with phi because phi is the variable. In parametric vector we had taken t. So this phi angle I can say it is t. So it is a sin t I plus a cos t j. If I differentiate it, then it will become a cos t I minus a sin t k. Earlier it was a sin t I plus a cos t k. Okay. Now if I differentiate it to get the gradient vector or velocity vector, it will come as a cos ti minus a sin a sin t k. Okay. If that is the case, then what is the now if suppose the t is 0 means phi is 0. If phi is 0, then we have a cos phi. Okay, so the kind of the velocity vector equation is a cos phi t I minus a sin phi t k. Now if t is 0, if t is 0, then only we can see that only I exists. If t is 90 degree, then only k exists. So when it is 0, when it is 0, then only I exists. Means the velocity vector has this direction. When it is 90 degree here, then it is minus k. Then velocity vector is downward direction, vertical. Can we see that? So if I have a sphere, if I have a sphere and this is top, then at this point, if I have taken only xz plane and if I see the displacement vector, then from the center of this sphere, it is radial in this direction. If that is true, then the velocity vector gradient vector is a cos t or cos phi I minus a sin t k. So if t is 0, then only I component exists. So it is like this. This is gradient vector. Gradient vector is tangential at point where we are calculating. So here it is like this, and here that is xy plane, it is like this, vertical minus k downwards. Here this I direction, here minus k direction downwards. So that the gradient vector keeps changing like this in xz plane. Can we see? Okay. Now this is gradient vector, whereas radial vector would keep changing like this. This is radial vector, whereas gradient vector keeps changing like this. Okay. Now we had taken theta equal to 0. What about if I really take theta to somewhere? Okay. So if I take theta to some value, now we had taken theta 0 means xz plane. Now if I take theta to some value, then it will come in xyz plane completely. Okay, so probably we will see that how it can be, and then we will come in Cartesian coordinate system also. Then we'll come to 2D. It is 3D we have started, then 2D, and rather than a sphere, we will take example in kind of parabolic or paraboloid everything. So we'll continue this discussion that how gradient vector actually it looks. So we have taken Cartesian spherical coordinate system and then parametric vector. Can you see the neatness in parametric vector? We have radial component as the distance displacement vector, and then the kind of gradient vector is tangential to the surface. So clear cut, right? Means so nice it is. So we will proceed on this discussion calculating gradient vector. It looks mathematics is very easy, very difficult when we understand things not step by step. Means it is so minute that if you make a single mistake, then it will carry on at higher level and things will be awkward, clumsy, darkness, and means it is not clear. It will be kind of hazy. But if you are crystal clear at minute level, then once it goes broader, then things will be quite clear. So we are trying to kind of give some estimation as far as a spatial imagination or a spatial drawing is concerned. So for radial displacement vector, we have gradient as the tangential. So this is what we saw, but we converted this 3D into 2D in the XZ plane. We will see in the XY plane, XYZ plane, then in Cartesian coordinate system, and then in 2D also. Then we will change the sphere to paraboloid and 2D circle to parabola. So this discussion will carry on. So I believe it is interesting, and then we will see more on.